Okay, good afternoon, everyone. Just a final sound check. This is coming through loud and clear, I hope?
Yes.
Okay, good. Okay, so first of all, thank you to Richard for the invite to, I guess, share some of the work that we've been working on in terms of the area of soil carbon in grasslands. We've been working on this basically since 2012. There's at least 3 and maybe even 4 or 5 different projects that have a pretty major component looking at soil carbon. And I'm going to mention at least 3 of those today. I'm also going to hint at some of the other work that we're just starting on that may be of interest to you as well. So just by way of an overview, I guess, to begin, I want to just walk through what the general research objectives were that we had when we started this particular project. Are we getting feedback? I'm just checking.
No, we're good here.
Oh, okay. So the first objective is basically to quantify the size of carbon stores in these grassland environments, and the ones that our egg producers and beef producers in particular rely on so much. And one of the things that we wanted to do is look at obviously soil carbon, since that's one of the largest reservoirs of carbon, but we also wanted to look at some of the other components, so vegetation above and below ground, root and shoot components, and also litter. And I think I have some insight on that. And then the other piece in this is really to try to get a handle on whether, and if so, where and when livestock grazing specifically increases or decreases soil carbon. And ultimately, if we can identify the mechanisms responsible for determining and predicting, I guess, where, when, and how soil carbon might change, that in theory should provide a foundation for policymakers to develop incentives to reward ranchers for maintaining and hopefully increasing soil carbon storage. So that's been the overarching goal that we've been driving towards over the last close to 10 years now. Not quite, but close. So I'm going to just briefly go through the method so that everyone gets a feeling for the scope of some of the work that we're doing. So one of the projects is called the Carbon Benchmarking Study. We started that in 2012, ran it through to 2015. We looked at well over 100 grasslands across the province of Alberta. You can see the map here on the right side. Basically it shows very widespread distribution, all the way from the Medicine Hat region up into the Edmonton area, and then from the Saskatchewan border clear up into the foothills. So we had representation of a very broad range of soil and agroclimatic conditions, so different climatic zones and vegetation types. And a couple of examples on here. And within this study, we basically went and sampled areas under long-term exposure to grazing, and then areas outside, inside long-term exposures in which we could isolate what the removal of grazing for an extended period of time would actually do. And we looked at a whole suite of carbon pools, vegetation above ground, what was basically in the standing litter, what's in the surface mulch, which is basically organic matter in various stages of decomposition on the surface of the soil, mineral soil, and also the roots, so the top 30 centimeters. And then we looked at organic and inorganic carbon pools. One of the big strengths of this study is the very large number of study sites. It's not uncommon to see studies that report on 2 or 4 or 5 study sites, but not 100 plus sites. So that's a marked departure from what you've seen elsewhere. One of the limitations that we had, though, we were only allowed to basically assess soil carbon down to 30 centimeters. And the reason for that is because these are long-term sites that are being monitored by the Alberta government. These are part of the Rangeland reference area, and they didn't want us taking coring trucks in, which would have allowed us to go down to 60 or 80 or 100 centimeters. And we also did not have a specific test of stocking rate per se. This is simply looking at grasslands with or without long-term grazing. So something to kind of bear in mind as we work our way through this. There's a second complementary study to this that I'm also going to draw on, and this one is actually probably going to be of significant interest to the folks in the room. This is an investigation of 9 different community pastures across the province of Saskatchewan, with further stratification of sampling within 33 different paddocks. So those are basically pasture units or distribution units. One of the strengths of this data set is we had long-term 25-year cattle stocking rates. So very long window of stocking rates, so that we could get beyond this binary methodology of looking at simply the presence or absence of grazing. We also had deeper soil samples to roughly 60 centimeter depth, and again we were able to look at organic and inorganic carbon. And we also had associated range condition data, which is basically a detailed breakdown on plant species composition that would enable us to look at how the maybe changes in the composition of vegetation could influence those carbon levels. So that'll be important when we get into that. The third study I'm going to be drawing on is what I call the nutrient cycling study. This is basically looking at specific rates of litter decay or decomposition, and also the specific role of extracellular enzyme activities. And this took place at a subset of the Alberta sites. So there's 15 grasslands covering 3 different natural subregions. And one of the unique pieces here is we actually looked at the litter decay rates in different grass species with known differences in response to grazing. So we looked at, for example, species like foothills and plains rough fescue, which have a known history to decline under increasing grazing intensity. We also looked at other plant species that are known to increase under grazing. The reason we did this is we wanted to understand whether potential changes in species composition from one group of dominant plants to another could actually account for changes in nutrient turnover, including carbon cycling. And one of the species included in here is Kentucky bluegrass, which is an introduced grass, but very widespread across much of Alberta, Saskatchewan, and in fact into the Dakotas and elsewhere. Okay, and the very last study that I'm going to draw on is an agroforestry study. And you might be wondering, why am I including that in here? Well, this agroforestry study was done between 2012 and 2016. And it was done at 36 sites across north central Alberta. But it provided some pretty interesting insight into the effect of different land use activity on soil carbon properties. And the 3 comparisons you see here are the 3 systems that we looked at. One was a forest grassland silvopastoral system, basically a combination of naturally occurring aspen mixed with perennial native grassland. We also looked at either shelter belts, which are planted trees, or naturally occurring hedgerows in concert with adjacent annual cropland. And it's the annual cropland that will be very important within these results. Okay, so very first question. What is the role of grasslands in storing carbon? So how much carbon are we essentially storing? So I want to start out with the agroforestry study. So these are actually carbon stores within the top 10 centimeters. And I want to be clear, this is only the top 10 centimeters of soil. So our standing carbon stock in the top 10 centimeter varies from somewhere around 70 tons per hectare all the way up to over 100 tons per hectare. And interestingly enough, the agroforestry system that stores the most carbon is really the aspen grassland mosaic. So it's the one where both vegetation types within it are perennial vegetation types, one of which is perennial grassland. So it's the cropland component here. So the converted grassland that's now drawing down those carbon levels. In that same investigation, we actually looked at detailed changes in carbon dioxide flux, methane flux, and nitrous oxide. So all three of these are important greenhouse gases and contribute to what we call global warming potential. And again, here's the comparison among the systems. And what's very notable is that the pastoral system, in which we're combining a perennial forested habitat type with a perennial grassland type, to the lowest CO2 loss, the greatest methane uptake, which is a positive thing because it means we're removing that methane from the atmosphere, and the lowest nitrous oxide release. And overall, that leads to the lowest global warming potential. So that really highlights the importance of these perennial systems, both forested but also grassland, in really reducing our greenhouse gas footprint. Okay, in the Alberta benchmarking study, we see very similar pattern of results. This is the total carbon pool if we compare native grassland with our adjacent cropland land uses. And again, you see a marked decline under our cropping areas, ranging anywhere from 28% in the prairie region to as large as 45% in the parkland region. And this is very consistent with what we see globally, where land use conversion from perennial grassland into an annual cropland typically results in the loss of anywhere between 40 all the way up to 55% of soil carbon. So the take-home message here is that the maintenance of existing perennial grassland is one of the key tools that we have to help combat rising CO2 levels. Okay, also within the benchmarking study, we were able to look at the contribution of different pools. So whether it's vegetation or roots or organic matter, soil organic matter, to the carbon stock. So this graph basically shows that the native grassland has significantly greater total carbon mass in comparison to both the introduced forage, so that's tame hay or tame pasture, and the cropland areas beside it. And the two pools that stand out very conspicuously, in addition to soil organic matter, is that the native grassland has a much larger pool of dead vegetation on the soil surface, which amounts to as much or greater than 10 tons per hectare, and nearly 15 tons of inorganic carbon as well. And so those two pools combined, together with the greater soil organic matter, mean that these systems, these agroecosystems, basically are supporting upwards of 30 to 35% more carbon overall. Okay, question number 2. So what is the specific role of grazing in regulating carbon? And if we know the answer to this, can we make a recommendation on how we might change carbon over time? And the answer to this, at least based on the past existing literature, has been very mixed. Some studies suggest grazing increases carbon, some decrease it, some indicate no change. So there's no real consensus on this. So if we look at the Alberta benchmarking study site, the first thing that we noticed when we looked at soil organic carbon, we noticed that across our 106 study sites, that our grazed areas were actually higher in soil carbon concentration, particularly in the top 15 centimeters. And this response appeared to be largely independent of plant biomass. We saw a trend towards greater overall plant biomass in the grazed, but that typically wasn't significant. The only response that typically increased significantly was for biomass. So it suggests that it's perhaps the turnover of nutrients, not the amount of plant input, that may be regulating these differences in carbon. Okay, another thing that we noticed when we looked at our data set from Alberta We also noticed that the presence of long-term grazing actually reduced the abundance of woody plant cover. And this was particularly notable in the moister areas of the province. So on this graph here, you see the percentage of woody plant cover, and it's related to something called annual heat moisture index. Annual heat moisture index is basically a measure of aridity. The driest areas of the province would have AHM levels of 40 to 50, and those would be found in the Brooks area, so similar to Swift Current down in southwestern Saskatchewan. Areas of the Parkland, say in the Saskatoon area and the Edmonton area, Stettler area, Wainwright, those were in that 30 to low 40s area. And the wettest environments, pardon me, are found over on the far left side of that graph. And what's very apparent is that the presence of long-term grazing is helping suppress woody plant cover. And so we started wondering whether that in and of itself could explain some of the differences in soil carbon that we were seeing. And indeed, when we took sites that had more than 10% shrub cover out of our initial analysis, we found that the remaining 73 sites no longer had a significant difference in soil carbon concentration. So you can see the difference here, about 1.29 versus 1.18. The other thing we noticed, though, which is that these very wet grasslands also had a greater abundance of exotic plant cover. And exotic plant cover, I mean species like Kentucky bluegrass, like smooth brome, like white clover and Alsite clover. So some of them are valuable agronomic species that are having a footprint. You can see that green arrow basically pointing to that 10 to 20% in exotic plant cover, particularly in the wetter parts of the province. We also noticed that there was generally higher plant species diversity under grazing. And so plant diversity represents the total number of different plant species that we typically find within these grazed grasslands. This is not uncommon because we know that some grazing is actually critical to maintaining a more competitive balance, if you like, among all the different plant species within these grasslands. And so increases in plant diversity attributable to the ongoing presence of grazing could actually help enhance soil carbon. So if we look at the relationship between herbage biomass and the abundance of introduced plant species, we see a general positive relationship between the proportion or the footprint of our introduced or exotic species and herbage biomass. And interestingly, this positive relationship occurred regardless of whether these grasslands are grazed or not. So it suggests that these introduced species may actually be adding not only through greater productivity, but that may translate into greater carbon stores within these systems. And if we look directly at soil carbon concentration, again we see a significant positive relationship between the proportion of introduced diversity comprised of these exotics and soil carbon concentration. So again, is this coincidence or is this cause and effect? That's really the question. So I want to switch gears now to looking at the Saskatchewan data, because the Saskatchewan data give us the ability to further explore this influence of stocking rate and plant compositional change. So in this graph here, what I've basically done is separated out the dry mixed grass, the mixed grass, and the mesic mixed grass sites. And what's very apparent is that obviously the mesic mixed grass has the highest stocking rates as you would expect. Higher rainfall, higher biomass, higher forage availability, therefore supports higher stocking. That also is associated with lower range condition in general. One caveat here though, range condition as measured here and reported represents nativeness. And nativeness excludes by definition some of those introduced plant species. And some of those introduced plant species may well be contributing to biomass increases and therefore carbon increases, as I'll show you shortly. Another property that's fairly important within the Saskatchewan sites that I wanted to share with you is just how much of the soil carbon is actually within the inorganic carbon. So the total pool of carbon was anywhere between 150 and 200 tons per hectare. And generally, almost a third of that carbon was comprised of inorganic carbon. You can see it ranged here from roughly 28.9 all the way up to 32.5%. So the inorganic carbon alone was 50 to 60 tons per hectare, and this is to a depth of 60 centimeters. So very large amounts of carbon and also inorganic carbon. Okay, so this is maybe the most important graph that I'm going to show you today. This is the relationship between carbon mass in the top tip 60 centimeters of soil and what I call mean stocking rate normalized for precipitation. And the reason we normalized is because we know that areas that are wetter are going to produce more biomass, and we expect them to therefore support higher stocking rates. So we had to adjust that somehow. So we basically created a normalized stocking rate index. And what's notable here is that all three of the relationships remain positive. Soil inorganic carbon is the bottom line, soil organic carbon is the middle line, and total soil carbon are all positively related to normalized stocking, which suggests that there's a positive relationship here between the amount of grazing going on and carbon within these agroecosystems. So when we dug into possible explanations as to why this might be occurring, if you recall what I said earlier, that more heavily grazed grasslands, even though they were grazed harder, they tended to have more carbon, but that's despite lower condition. But the lower condition is really nativeness. If we look at factors like introduced plant cover, we actually see very close alignment between the abundance of introduced plant species and factors such as total carbon, soil organic carbon, and inorganic carbon, which is further adding credence to this notion that a plant community shift occurring because of higher stocking rates may indeed be accounting for the higher soil carbon. In particular, if you look, so this is called an ordination graph. But the most important thing on here is if you look at the far lower right, you'll see a species called Poa pratensis. That's Kentucky bluegrass, which is the same dominant species that we see throughout much of southwestern Alberta, and coincides very closely with increases in soil carbon in that region. Okay, so what biochemical mechanisms may be explaining these grazing impacts on soil carbon? And does plant species change lead to altered carbon accumulation? So now I'm going to dig into some of that nutrient cycling work that we did. So what we did in our litter bag study, we wanted to know whether grazed environments led to faster litter decay and therefore carbon cycling. And indeed, that's exactly what we did find. So the two graphs on the right side here basically show decay of litter in environments that are either grazed or non-grazed over an 18-month period. And within both the foothills fescue of southwestern Alberta, so a relatively wet environment, and the aspen parkland of central Alberta, which is also a fairly moist environment, we saw more rapid decay within those grazed grasslands. So the question is then, what's the fate of that carbon? Is it simply being broken down and released back to the atmosphere, or is it being broken down very quickly and incorporated into the organic carbon pool within the soil, where it can be sequestered for an extended period of time? We also found, and this is in the graph in the lower left, we also found marked differences between plant species in decay rates. In fact, the Poa pratensis, the Kentucky bluegrass I was telling you about earlier, actually experienced the most rapid turnover of litter of all the grasses that we actually looked at. In contrast, many of the native grasses had very slow decay rates, suggesting that that in turn may not contribute as much to carbon biogeochemical cycling. And when we looked at the activity of carbon liberating enzymes, so these are the specific enzymes that are responsible for the turnover or breakdown of carbon from the litter pool, translating it into the subsoil or topsoil and contributing to long-term carbon storage, we see differences among the different plant species. In particular, bluegrass is one of those species that again stands out, particularly at the 18-month period where the enzyme activities associated with carbon turnover remain relatively high, particularly in comparison to some of our other grasses. Okay, so I'm just going to kind of have a summary slide to kind of pull some of this together, what we know. And then I'm going to finish up with some additional work that we're doing right now. So it's safe to say that our perennial grasslands, particularly in comparison to the annual crop environments, contain very large amounts of carbon, often 30 to 40 or 45% more carbon. And that includes carbon within the organic pool, inorganic carbon pool, but also within the litter and mulch. It's often a sizable component. Changes in vegetation composition, and in some cases even independent of grazing, appear to regulate grassland biomass productivity, but also associated carbon levels. An abundance of introduced species, particularly Kentucky bluegrass, but there may be others that we haven't identified, and in turn, greater plant diversity in general within these moisture grasslands, which is of course facilitated by higher cattle stocking. They actually enhance soil carbon. And that's one of the factors that we're continuing to push forward on as our research unfolds. I want to mention a few other studies. I know I got just a couple minutes left. So some of you may even be aware of this. I'm a member of a large group of researchers working on a project that we call the Adaptive Multi-Paddock Grazing Enterprise. This project is basically doing an assessment of 60 ranches across Alberta, Saskatchewan, and Manitoba, where we're looking at how adjacent differences in the type of grazing system, meaning the frequency of grazing, the length of rest periods, and so on, they change everything from plant biomass, plant diversity, to carbon storage in the soil, greenhouse gas flux, and so on. This is, again, a very large-scale investigation. It's happening on commercial working ranches, and they're distributed widely across the 3 prairie provinces. So that work is about halfway through right now. We also have studies that are looking at the specific role of differences in microbial diversity and composition, and how that in turn might change, for example, soil carbon cycling, either accelerate carbon cycling or nitrous oxide release or methane release, and so on. Because we know that soil microbes are the ultimate mediary, if you like, of carbon cycling of both litter and soil organic matter. If we can understand this, then we might have further insight into predicting where, when, and how grazing actually will change soil carbon and associated greenhouse gases. Because again, the goal here is predictability of carbon in relation to grazing. And the last one is also looking at potential impacts of defoliation on carbon flow. And some of you may be familiar with a lady from Australia named Christine Jones. She's a big advocate of this notion of the liquid carbon pathway, that defoliation may trigger carbon release through deep exudates into soil from roots, and that in turn may feed soil microbes, and that may create a feedback loop that leads to significant carbon storage at depth. So this is a small kind of pilot study that's being done to try to understand whether indeed different defoliation patterns change carbon flow, especially at depth. And if it does, then we can follow up with more detailed studies to understand that. Okay, so lots of folks have contributed to this. Some of the main players are Cameron Carlisle, Scott Chang, Mark Boyce, Daniel Hewins, who I believe has given a talk to your group in the past, and many others. There's a small army of graduate students and summer students that have been critical. So I'm happy to take any questions. I believe I've got some time for questions, and I'll answer them as best I can. If I'm not able to answer them here today, you can always shoot me an email, and I will do my best to answer them outside of this forum as well. So thank you.
Okay, thank you, Dr. Moore.